Okay, so let's look at a case where maybe we have like a syringe or something where there is a container, a cylinder maybe, and it narrows to a much smaller cross-sectional area. So there's my horrible drawing, but maybe this is some sort of syringe or something of that nature, and it's full of fluid. So here is my fluid. Here we go. We've got a fluid in there. And there's a cross-sectional area here, like the end that the plunger goes in when you're pushing fluid through a syringe. So this I'm going to call A1. And this little end is much smaller. If it's like an oral syringe, it's just a small, tiny little area, maybe like the syringe used to give a child medicine or a cat or a dog. There are antibiotics or medicines. Maybe you've had that experience. Or even a syringe where the needle point at the end is open, but it's little bitty tiny. So if this is a non-compressible fluid, what does that mean? What does it mean by non-compressible? What do you think? So if the density doesn't change because the fluid is non-compressible, then if we put 1 drop of fluid in this side, what must come out the other side? 1 drop of fluid. So the volume that goes in must equal the volume that comes out. And if we can't compress it, then this must also happen in the same amount of time. So the volume flow rate is continuous. This is called the volume flow rate. Any questions so far? Volume flow rate? Volume per time? Now let's look at a specific piece of this fluid. So I'm going to look at a chunk of this fluid right here. And you can't see this backside right there. And it has the same cross-sectional area as the end of the pipe. And maybe it has a little length right here I'm going to call L1. And as the fluid flows through to this more narrow section of the pipe, what's going to happen to this volume? Is it going to stay the same? Volume flow rate's the same. What's going to happen to its shape? What do you think? So as it moves through the narrow pipe, it gets longer. So L2 would be longer than L1, so that these two volumes could be the same. How do you find volume of like a cylinder? Base times height. How about let's write it as the area of the base times the height, and in my case it would be A1 times L1 over T. And then for our narrow section, we'd have A2 L2 over T. And if you had to find the area, this is the cross-sectional area, so it was pi r squared. Or if it were a cubic shape, it would be length or side squared, or if it was a rectangle, it would be length times width, whatever you need to do to get to the area of that cross-sectional area. You might have some sort of container that is in a shape like this, and then it narrows. Pretend like I'm really awesome drawing, but maybe it narrows later to something like that. So you would have this as your cross-sectional area there. And this one that's drawn real ugly would be your cross-sectional area at the end, but it could be rectangular shape. Okay, what is length divided by time? Or, speed. So could I write this as A1, V1, and A2, V2? And this came from it being volume per time. So the volume flow rate, volume per time, is equal to the area times the velocity. Remember when I told you you'd have equations with volume and velocity together? So be careful about your symbols. So this is called the volume flow rate. It would be measured in what, meters cubed per second. This is our cross-sectional area. Measured in what, meters squared. And this would be the speed of the fluid. Measured in meters per second. What do you get when you multiply meters squared and meters per second? Yeah, meters cubed per second. So does that work out unit-wise, that volume per time is area times velocity? So you probably have a volume flow rate continuity type situation at your house. Probably like in the shower, there's this thing right here, and maybe this pipe was like that. You got all these little bitty holes. What's the purpose of having all those little bitty holes? So what does it change? If you take the shower head off, what's the water like? It's like droopy. Then you put the shower head on, and what does it change? It changes the total area that the fluid has to flow through. It reduces the area. So by reducing the area, what do you change? You increase the speed. So you get this V where this was V. Have you ever needed to increase the speed or maybe the distance, and you're using a water hose, a garden hose, and you didn't have the spray trigger on the end? What do? If you don't have the spray trigger? Oh, you can put your thumb over it. By putting your thumb over it, what are you changing? You're changing the cross-sectional area, so you change the speed. So by reducing the area, we increase the speed of the fluid. So that is a everyday example of your continuity. Now, when fluid flows through a pipe, there's other things acting on it too. Let's look at maybe here is a pipe and it goes through a change in height. So this could be the water tower. Represent the end of the water tower where the water comes to your home, and this is the faucet in your kitchen or something like that. The water tower is up really high, like on Jones Bridge Road. We can see the water towers. No? They say Fulton on them? Okay. Anyway, we'll look at the midpoint of the pipe because some water or fluid particles are above and some are below, but on average they're here in the middle. So I'm going to fill it full of fluid there. So here is my average point there. Those are just dotted lines. I'm going to call this Y1 and this is Y2. And this end has a pressure acting on it here. I'm going to call it P1. If it's open to the atmosphere, the atmosphere is pushing down on it. When you open the faucet in your home or in the classroom, the faucet is open to the atmosphere, so that would be P2. So that's, in this case, it may be or it could be a pressure that's being applied by a pump or something like that, but there's a different pressure here than there. And in general, what would the fluid do? It's going to move. It'll go down. Why? What is it? There's gravity, but what do the water molecules have up here? Oh, potential energy. What's it converted to down here? Oh my goodness. We can look at the change in energy of a fluid system. So maybe up here it's moving too. So we'll call that V1. And down here it's also moving. That's V2. So we have the height of the pipes, and we have the speed of the fluid flowing through the pipes, and the pressure applied to the either end of the pipe. Now, if work is force times distance, and pressure is force per area, then would work be pressure times area times distance? Now, what's area times distance? An area times a distance. An area times a distance. That gives you volume. So then the work done by a force that causes pressure would be pressure times volume. Now, when we studied energy and mechanics, we had conservative forces and non-conservative forces. Our conservative forces were gravitational force and the electric force that we haven't studied yet. And in special cases, our spring force was conservative. So do you think that the force that is causing the pressure is conservative or non-conservative? We have certain conservative forces that we've listed. So it must be non-conservative because it's not gravitational force causing the pressure, and it's not necessarily it's not a spring force, and it's not an electric force. So we have the work done by a non-conservative force. Do you remember this? This is like reviewing for the your final here. Work done by the non-conservative force is equal to delta K plus delta U, the change in potential energy. All right, so then the difference in the two pressures. So P1 is in the positive direction in our picture right here. P1 is causing, is putting positive work into the system. P1 times V, but P2 is doing a negative work because it's trying to hold the fluid back from running out of the pipe. Then our kinetic energy would be final K2 minus the initial kinetic energy, so the kinetic energy of the fluid at point 1, plus U2 minus U1. Is that okay? Now let's get all of our 1s and 2s together. This is going to look like a big party. So P1V plus K1 plus U1 would be equal to P2V plus K2 plus U2. Did I do that right? But remember, density is mass per volume, so mass is density times volume. So as we substitute, anywhere we have M, we're going to put a rho times volume. So pressure 1 times volume plus 1/2 rho V for mass, velocity squared. Remember I told you we'd have V for volume and V for velocity together? Yay! Plus rho volume GY1 is equal to P2V plus 1/2 rho volume velocity 2 squared plus rho volume GY2. What do you notice? Oh my goodness, looks like I can divide by the volume on both sides because it is multiplied by every single term Boop. Well, that looks a little bit better. So then let's write down our simplified version. P1 plus 1/2 rho V1 squared plus rho GY1 is equal to pressure 2 plus 1/2 the density, speed at the bottom squared plus density, acceleration due to gravity, and the height of the bottom. And that, B's and G's, is Bernoulli's equation. I like to think of it as the conservation of energy for fluids. It's not energy because they're all in Pascal. It's like Pascal plus Pascal plus Pascal. So it's all in pressures, but it comes from that conservation of energy for a fluid that's moving. Now there is a special case, and let's look at that.